All right, hi there, 114. I've been getting a few questions for homeworks 5.1, 2, and 3, so I just wanted to make a short video showing you a few of the selected problems from the homework that I'm hearing about. All right, your job is to try them on your own first, as always, okay? Make sure you read every question, understand the context or what they're expecting from you. Make a plan, try it out. Enter in an answer. It's okay to get it wrong. You have multiple tries. Okay, then you can watch the video for that selected problem. Okay, so we're going to be talking about logistic functions and power functions. All right, so stay tuned. When I first read this problem, I felt like it was pretty straightforward once you understand the format of the formula for logistic growth. All right, I went ahead and I wrote the formula here. N equals K over 1 plus BE raised to the power of negative RT. Okay, they tell us the carrying capacity is 1500. Well, it just so happens that K is the carrying capacity. It's always that numerator value of K, carrying capacity. And you can see I went ahead and put the answers up for this one. That 1500 is in the K position. All right, so the carrying capacity just gets put straight into the formula, substituting for K. They give us an R value, all right, that's the intrinsic growth rate. That's going to get substituted directly into our formula as written, 0.02. So where I have E raised to the power of negative RT, I'm going to have E raised to the power of negative 0.02 T. Right? Don't lose that negative. That negative changes everything. Finally, it tells us that the initial population is 300. We use that initial population in combination with the carrying capacity to figure out this constant B value. I gave the formula for it in class. It's also in the textbook in section 5.1. Right, if you look for the formula for the logistic model, you'll be able to get more information there. But we can use this formula directly. We know what K is. K is the carrying capacity. All right, so I'm just going to substitute some values in here. K is the carrying capacity, which with my numbers is 1500. I'm dividing by N of 0, which is the initial population. It's the population when 0 years have gone by, which is the initial population of 300. Then I have to subtract 1 from that. We can do this division first. 1500 divided by 300 yields 5. Subtract 1, we get 4. Straight away in the formula, you can see that that 4 rests in front of the E, just like it would in this formula. Now, don't be fooled by this form where I have the plus 1 swapping places with the BE to the negative RT. It's not changing anything, right? I can add in any order. But that's how you're going to construct the formula for logistic growth using that given information for problem 1. Still in section 5.1, I'm looking at number 2 now. You're asked to find the formula of a certain number associated with the logistic formula. The only numbers that you could be looking for really are K, B, and R, because those are the constant values that are in this formula. T and N are variables, right? So those can change. They don't have constant value. We are given a value for R. That's the intrinsic growth rate. R equals 0.3. What would be the growth factor in the absence of constraints? We only get a logistic model if we begin with the exponential. Here's our exponential model, right? PA to the T equals our function. We only get the logistic model if we have constraints, if we can't grow forever in an unbounded way. Sure, we start off looking exponential. We reach our maximum sustainable yield, our optimum yield, and then we start going towards that maximum carrying capacity. This is our logistic model. It's going to be a little harder to fit under here, but let me see if I can do it. BE to the negative RT. Okay, K-vert. This is our logistic model. So if we don't have those constraints of carrying capacity, of limited resources, we have exponential growth. So what we're really looking for is the A value. Remember, that is our growth or decay factor. In this case, it's a growth factor. So what we do is we use one of two formulas to go back and forth between A and R. If I have R and I'm looking for A, I'm going to use this first formula. If I have A and I'm looking for R, like in problem number 3, I'm going to use the second formula here. Okay, so right away, we have a formula that we can just plug into or substitute into. I'm looking for A, my growth factor in the absence of constraints, equals E. Remember, we know that's just a constant number. You can find that in your calculator in the first column. Second ln will get you there. E raised to the power of R. Well, we know the value for R. I'm just substituting that into my formula here. And what I get in my calculator, what pops out is 1.3498 blah, blah, blah. It just keeps going. What I need to do is listen to the instructions. Round your answer to 2 decimal places. We look at the third decimal place. Is it greater than 5? All right, it's time to round the second decimal place up. You can see I left the key on. 1.35 is how this was rounded, from 1.349 to 1.35. That is the growth factor in the absence of constraints. All right, let's scoot on down to number 3, still in section 5.1. We have the formula. They're just showing us again where these values are placed into the formula and what they're referring to when they talk about an R value. Okay, they can't just start talking about the letter R and not tell you where it comes from. It comes from the logistic model in this case. They tell us in the absence of constraints, I'm automatically thinking exponential when there are no constraints. Okay, in the absence of constraints, a population would have a yearly growth factor of 1.15. That's my A value from the exponential model. What is the corresponding R value? This time we're rounding to 3 decimal places, okay? You probably have a different growth factor in your own problem, but this is how you would do it with my numbers, okay? There's a formula at the top. When I'm looking for R and I have A, I'm substituting my A value into this formula number 2 at the top. Right, you can put that directly into your calculator. ln is in the first column on the left of buttons, and we're doing ln of 1.15. What I get is about 0.13976 ... I need to round to the third decimal place, so I consider this one the fourth decimal place. Is it greater than 5? It is, so I round up. I'm rounding 9 up to 10. So this becomes a 0. I carry the 1. I'm taking 139 and I'm rounding it up to 140. Right, that's how, and I left the key on here, that's how we get an answer of 0.140. Make sure you have 3 decimal places there. This problem, number 11 from 5.1, has a very long introduction, and I find that students will sometimes think they can just skip through, look at the numbers, and try to come up with an answer. For these logistic models, it's pretty complicated. Okay, the formula that we're dealing with it's long, and it has a lot of moving pieces here. We have a carrying capacity divided by 1 plus B, if you remember. We have a little formula for solving for B, times E raised to the power of negative RT. Look at all of those different pieces. If you just try to plug in different numbers in there, you're going to have a really hard time figuring out what the formula is going to be here. Okay, it's going to be very tough. But if you read it and you pay attention to what these numbers mean, it's going to help you a lot. We have a PTA. They want to increase participation, the population of the PTA. All right. We start with 17 parents at the meeting. That's my initial population. I start with 17 parents. Suppose the school board plan results in logistic growth. That means there is a carrying capacity, right? That means that there is a limited number of resources that they can support, or a number of parents in the PTA that they can support. That level that they can support is 34 parents. That's our carrying capacity. If we have more than 34 parents, well, we can't have more than 34 parents. The PTA can't support it. The school board can't support more than 34 parents. In the absence of limiting factors, the school board believes its plan can increase participation by 10% per month. That's a percentage increase. Remember, from exponential functions, that would be our absence of limiting factors, population grows without any limit. It grows exponentially, okay? What we have is A equals 1 plus the percentage growth. Well, the percentage growth is 10%. So we are really growing by 1 plus, we're going to change that from a percent to a decimal, 0.10. That A value, the growth factor, if we were unlimited in our growth, would be 1.10. I'm just adding those numbers together, that percentage there. Okay, let M denote the number of months. Okay, since the participation plan was put in place, the number of months, so this would be like T in our previous models. I'll go ahead and fix this. I noticed I made a mistake up here in our model. That T is actually an M because the M is our independent variable. All right, so, and let P be the number of parents attending the PTA meetings. All right, parents. Let's see if we can make this model answer the questions as we go. What is the carrying capacity for the logistic model? Well, it's the maximum number of parents that this school board can support. It's 34. That's directly from context. Find the constant B for the logistic model. Let's do that. We have the formula B equals the carrying capacity divided by the initial population of the PTA minus 1. All right. Our B value then is 34, which is our carrying capacity divided by 17, which is our initial population, and subtract 1. Well, pop it in your calculator. 34 divided by 17 is 2. 2 minus 1 is 1, and you can see in the key, that's how they got the answer of 1. All right. For part C, we're trying to find an R value for a logistic model. This is an intrinsic growth rate. This is not R from exponential functions, okay? This is different. This is the intrinsic growth rate. The intrinsic growth rate can be found if you have R, ln of A will give you the intrinsic growth rate, all right? And you're gonna wanna do that to 3 decimal places. Well, we already figured out what our A value is. So let's go ahead and pop this in the calculator. ln from the first column of buttons on the left of your calculator of 1.10. All right. When I pop that into my calculator, I get a very long decimal, 0.09531 ... a whole bunch of numbers. It just keeps going, right? It says round to 3 decimal places. Here's my 3rd decimal place. Let's look at the 4th decimal place. It's less than 5, so I'm going to round down. All right, so you can see we're rounding down to 0.95. And that's how they got the intrinsic growth rate here, 0.095 in the key. Finding that logistic model of P versus M, it'll be relatively simple now that we have all of the pieces, all of the constants for the formula. All right, let's go up to the top of the screen and we are going to construct P of M. All right, it is a ratio, so I'm going to go ahead and put that division bar there. It's a ratio. What goes up top? The carrying capacity, K. Right, I'm just making substitutions over into the final formula. 34 is our carrying capacity. In the denominator, we have 1 plus B. We already calculated B. B is 1. Right? 1 times e raised to the power of a negative RT. R is 0.095, and M is our variable here. Okay, we're not using T here, we're using M, and I've been tricked. Hopefully you didn't fall for it. Okay, here's our formula. It's exactly what they have in the key here. It's all of, that's why they ask you A, B, and C first. It's so you have all of the pieces before you try to make your formula. They're checking. Do you understand where all of those pieces come from in the long context? All right, we're here in 5.2. I'm doing question number 4. I like to do this problem. I have gotten a couple of questions on it, so I wanted to address it here in the video. We have a car that is driving along at a certain speed. All right, so I have my car. Let me see if I can do any sort of sketching here. I have a very poorly drawn car, and that car is driving at a certain speed. Okay, again, very poorly drawn car here. They're driving along, and when they hit their brakes, they start to leave skid marks. Okay, so they hit their brakes, and the rest of the time that they are moving forward with those brakes down, it leaves a skid mark on the road. That skid mark is being measured here, having a length of L. Okay, that's in feet. I believe it's in feet. Let me make sure. Yes, it is in feet. Now, depending on how fast this car was driving, that tells us how long those skid marks are going to be. So L, the length of the skid mark, depends on the speed that you're going. Okay, if you're going really fast, you're going to continue moving forward longer than if you were going very slowly. That skid mark would be very, very short. So for me, it makes sense. Hopefully, if you think about this, being in a car going faster takes longer to stop. Hopefully that makes sense to you as well with this model. All right, so let's look at the power function that they gave us. Straight away, I see a little bit of a problem that I want to address. Maybe it stopped you in your tracks when you were working this problem. What I have is 1 divided by 30 times h times s squared. I count 3 different letters here. I count an L, I count S, and I count H. But if you keep reading, you'll see that H is actually a constant. It's not a variable. Okay, and that kind of reduces the difficulty of the problem because we're really just dealing with L as a function of S, not S and H. Okay. The friction coefficient, this comes up in a Physics 1 course. The friction coefficient depends on the road surface, okay, and the conditions that you're driving in. So if you have dry concrete that you're driving across, the friction coefficient, okay, it's sort of gripping your tires, is about 0.85. So let's rewrite this formula. L equals 1 over 30 times, it's not H anymore, it's just a constant value, 0.85 all times S squared. I'm going to toss that in parentheses because when we use our calculator, we want that in parentheses. So 1 divided by 30 times 0.85, that's just a number. All right, let's go ahead and figure out what that is. I've got 30 times 0.85. What does that give me? 25.5. I'm just going to simplify that even further. So the function that I'm dealing with here, L of S, equals 1 divided by 25.5 times S squared. Right? My coefficient here, my C value, is 1 divided by 25.5. So in part A, it asks us to apply this formula. If a driver is going 65 miles per hour on dry concrete, all right, with that friction coefficient, H, they jam on the brakes and skid to a stop, maybe there was an emergency of some kind, how long will the skid marks be? All you're doing is plugging in or substituting in 65 miles per hour for S. So go ahead and pop that in your calculator and see, do you get 165.69? I popped it into my calculator, L of 65, because S equals 65. 1 over 25.5 times 65 squared. I popped that in, and what came out of my calculator was not the exact same answer they got, but I did have a decimal that was pretty darn close. Okay, and it looks like they give us a hint to round to 2 decimal places. So once you round, you'll see that you do get 165.69, and that's the length of the skid mark in feet. Okay, if you're going 65 miles an hour, you slam on the brakes all the way to a stop, the skid mark that you'll leave on the road will be about 165 feet long and some change. All right, we can look at part B. It's asking you a different question. It's asking us to think of this question kind of inside out. A policeman is investigating an accident that occurred on dry concrete. The skid marks, I'm going to work this part in pink, the skid marks were 112 feet long. the speed limit in the area, S better be 60. That's miles per hour, okay? Is the driver in danger of getting a speeding ticket? Okay, we can see the answers already on the screen, but we need to understand the reasoning. Okay, I was working this out with another student and they had completely different answers. So you really do need to pay attention to what your numbers are and work them out with your numbers. Anytime you have a formula for your dependent variable and you have another value for that same independent variable, we use the crossing graphs method. All right, and what that consists of is making one of those lines into Y1, and one of those lines into Y2. Then we're going to graph them and we're going to see exactly where they intersect. That intersection point will give you the speed that we were going, okay, for a length of 112 feet. Now, I'm going to take a second and put that in my calculator. I'm going to pause it. You can pause the video so that you can do the same. When we come back, I'm going to briefly walk through the rest of the steps. All right, so once you have your Y1 and your Y2 into the calculator, you're going to want to adjust that window, okay? Because if you can't see where those two functions intersect each other, you're not going to be able to use the intersect calculation option, okay? You have to be able to see it in the window. That's the only place the calculator checks. So if you just hit window, we think very carefully about what we need to show on our window. X is representing the speed. X represents the speed. I cannot have negative speed here, so I'm going to start my X-min at 0. I'm thinking that this driver is going to be somewhere around 60 miles an hour. They could be speeding though. Okay, we want them to go 60, but they could be speeding. Maybe they're under the speed limit. I don't know. So I'm going to first look at a window. I'm going to go a bit over 60. I'm going to take it all the way up to 65. That's miles per hour, just in case they're speeding by up to 25%. With my Y min, think about that as length. We can't have a negative length for these skid marks. And then if we think about the Y max, they already told us how long the skid marks are. We entered those into our calculator. I have to be able to see a length of 112 feet. Let's make it a little bit longer, right? So we're not just at the edge of our calculator screen when we're looking. I'm going to take it up to 120. Once you've adjusted your window in this way, you can hit graph. That's going to give you a nice visual. And then you can hit second trace 5. Second trace brings you to your calculation menu, and option 5 is the intersection calculator. Okay, it's going to ask you 3 questions. It's going to ask you press enter on the first function, press enter on the second function, and then you're going to sort of arrow a little bit left or right to move towards the intersection and press enter. That's called your guess. Okay, it's going to give you a couple of values out. It's going to give you an X value, which is really a speed, 53, approximately 0.44 for my numbers, and a length of 112, or a Y value of 112. I'm throwing those together as a point so that we can see this is an S value and this is an L value. In my context, the speed limit in the area was 60 miles an hour, but the driver was only going 53.44 according to our skid mark length function. So it appears that the driver is not in danger of getting a ticket because the math is on their side. All right, they were going about 53 miles an hour here. When I was working with another student, their speed limit in the area was 50 miles an hour. So if the person here was going 53 miles an hour in a 50 mile per hour zone, they would have been in danger of getting that speeding ticket. With this problem, I made part C worth 0 points because we're not going to talk about the homogeneity property of power functions. If you want to know more about that, it is in section 5.2, and you're welcome to go look at that or send me any emails if you have questions, but it will not be tested on the exam. Okay, Okay, so for the last part of this video, we're going to zero in on section 5.3, which is all about regression. Particularly, it's all about power regression, right? So trying to find a power function of best fit. However, this chapter or this section has you look at the data and compare models of different kinds. So like in number 1, we're going to get one data set. We're going to try to find a linear model that fits the data. Whatever the calculator gives us, it considers that to be the line of best fit. That's what we're going to do first. Then we're going to try to fit a power model to that data. We're going to do power regression, and we're going to see which is best fit. Okay, which one is closest to the actual data? We're going to see which one is better. Okay, so as with all regression problems, in fact, all problems that give you a table of data, all right, you want to hit your stat button. We've got the science of data is statistics. So hit stat, select edit, because we need to edit some lists of data. I want you to let your L1 data be all of your X values. So 6, 6, 9, 104. You want to fill in all of your L1s with X data, all right, all of the X's. Your L2 data should be corresponding Y values from the table. So 6 has a corresponding Y value of 1.5. 6.9 has a corresponding Y value of 2.6. 104 has a corresponding Y value of 2.8. Okay, continue in until you have all of your corresponding Ys filled out in your L2 list. Now, once you do that, you're done editing. We need to go to the calculation menu. So you're going to hit stat. We need to do some statistical calculations. You're going to hit the arrow that heads to the right because we need to get away from the edit menu and into the stat menu. In my calculator, it's option 4. We're going to select LinReg, which stands for linear regression, AX plus B. And what do we get? Our output is A equals 0.00655, blah, 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 lots of numbers after that. And the B value here is 1.8872, ... Okay, now what's important here is that you note where the A and the B go in the formula. I have AX plus B. Some of you may have A plus BX. So pay attention to where those values are. In my problem, my linear model will be Y equals A. I've rounded to 3 decimal places as indicated by the problem. X plus B, 1.887. That's how we're getting this answer in the key, and I'm leaving the key on so you can see exactly what the final answer is for these. If you wanted to plot this data alongside the model, you're going to go to your Y equals menu and let Y1 equal this formula that you just typed in as your answer for part A. Okay, all of your table data is still saved into L1 and L2, so all we have to do is turn on a stat plot. All right, so you're going to hit second, Y equals, that's at the top left corner of your buttons. Select plot 1, press enter. Turn it on, press enter. Everything else is exactly the way it should be, and you're just going to hit graph. Now, if you cannot see all of your data points, you're not going to be able to decide if this is a good model. So what we do is, let me write this down for you. We hit zoom, which is a button at the top of these. It's the first row of buttons below the screen. And we're going to hit 9, which is zoom stat. Okay, zoom stat. And what that does is it makes sure that you can see every single data point that you gave it, all the way through 279 in the X, all the way up to 3.5 in the Y. It fixes the window for you. So now you can select the appropriate graph, which demonstrates the data along with the linear model that you found. All right, moving into part B, what you're going to see here is that we are trying to use the same data, but this time model it using a different type of function. We want to find a power model. Now, do not go delete the data. Do not do a RAM reset. Okay, do not do that. What you want to do is leave all of that data alone. If you hit stat edit, you should still see your data there. Now I'm going to hit second mode to go back to my normal screen, but this time, since our data is already in the formula, we're going to hit stat. We're going to arrow over to the right, which is going to take us to the calculation menu. And I believe in my calculator, it's option 0, but it's called Power, PWR, Regression, REG, Power Regression. So we're just doing the exact same thing with linear regression. Oh, I lied. It's option A. Sorry about that. Option A. Option 0 was exponential regression. Here we're doing a power model. So let's do that power regression. Scroll down, hit enter. L1 is your X list. L2 is your Y list, just like before. Let's calculate it. Here's what my calculator popped out. Y equals AX to the power of B. That is the form of the calculator model. It tells me that A is, if I round, 1.01 times X raised to the power of B. If I round, I'll get 0.221. That's with rounding. Okay, and you can see that's exactly what they're getting as their power model over here. Stat calc, calculate the power regression. This is what it returns to you. You need to go back to your Y equals here. Go back to your Y equals button. Let Y2 equal 1.01x to the 0.221 power. All right, so now go look at that graph. It's already going to be zoomed in to the perfect screen because we did a zoom stat before. Okay, so all of the data can still be seen. You can see that if you were to compare which model does a better job of which type of model, the linear or power, does a better job of fitting the data, you can see the power model does a much better job than the linear model. All right, and that's part C. You want to try to decide which model is the closest to the most points, and it's the power model. This problem is very similar to the last problem in that you need to hit stat because you have data. You need to select edit, which is the first option there. Let L1 be all of your X values, 3, 4, 5. Enter those in one at a time. Let L2 be all of the corresponding Y value or F values from the table, 1.7, 0.5, 0.3, 0.06. Look at that. Those numbers in the Y are getting smaller and smaller and smaller, right? That tells me that we have a decreasing power function. So, and that's when X is positive. So I know that I'm going to have some sort of function that is decreasing like this, and we know it's a power function, right? So it's going to have a negative exponent. That's what I'm expecting. And if you just look at the key, you'll see we do in fact have a negative exponent. When you enter in your data, you need to hit stat again because we have to do a calculation. So we're going to arrow over to the right to calculation menu. All right, this time I need you to select power regression because we're trying to model the data using a power function. Only way to get a power function out is to select power regression. All right, and the formula pops out directly. All right, if you round to 2 decimal places, you have your A value, you have your B value, substitute those into the formula. Cx to the k, okay, in this case it's going to be ax to the b if you're using your calculator. Substitute those in and automatically you can see the formula. And that's the beauty of regression. I wanted to go over this problem from 5.3, number 10, because we haven't talked about this since we talked about exponential models back in chapter 4. All right, and you can see right away the answer is going to be exponential model here. I left the key on, okay, but we can kind of talk about this a little bit more. A rumor is spreading, and you find that each day the number of people who have heard the rumor is 50% larger than the day before. Okay, so if you and a friend know the rumor on day 1, I add 50% to that. So on day 2, I get 2 plus 50% of 2, which is 3 people. You add 50% again, I'm adding another 1.5 people. So now 4.5 people know, which in the context really means only 4 people know. All right, but just looking at the numbers here, just trying to come up with a model. Then if I add another 50%, then 6.75 people know, and you could keep going. All right, you could keep going with that. This is just to get some numbers under your belt so you can kind of see what's going on here with the numbers. However, just consider this. Anytime you have percentage growth and there's no sort of upward bound on the number of people, in this case, on the number of people who can support the rumor, who can know the rumor. There's no upper bound on that. There's no limit on resources that are going to keep people from knowing the rumor. It's just knowledge. So what that means is that it's not logistic in any way, because that would imply that there's some sort of limit on resources. It's not linear, because that would be like just adding one person every day or every unit of time. And you can see that's not what's going on here. From day 1 to day 2, in this case, I added one person, but from day 2 to day 3, I actually added 1.5. And then the next time I added 2.25. And it kept going in that way where it's increasing every day. So it's absolutely not linear. The slope is not constant. Next, you might think that we have a power function, okay? Linear is a power function. Quadratic is a power function. The power function does not grow fast enough to capture exponential growth in this way. In fact, I want you thinking anytime you have percentage increase per unit time, you need to be thinking that means exponential model, unless you hear something about a carrying capacity, okay, because that brings it into a logistic model. But without any sort of cap on that, you have exponential growth, right? It had just been a little while since we talked about that, so I wanted to go over that one again. Number 11 is really just a continuation of our discussion with number 10, right? We have a rumor spreading. Each day that the number of people who've heard the rumor is 50% larger than the day before. So, as we mentioned before, we have an exponential model. Let me get my pen here. We have an exponential model. That's if we can grow without bound, without limits, without bound, without a limiting value here. If I can just keep growing and growing and growing, and there's always going to be somebody new to hear the rumor, that's exponential growth. However, listen to this new caveat, this nuance in this problem. Suppose the rumor is spreading across your college campus. So over at Buff State, this rumor is spreading, but it will never spread beyond the limits of the campus. How might this new information alter your choice of model? Well, think about it. How many people go to Buff State? I'm not sure the exact numbers. Let's say about 13,000 students go to Buffalo State. If the rumor never, ever, ever leaves, no matter how long we wait, it never leaves the college campus, then only 13,000 people are going to know this rumor. Okay, that's a max. So even if enough time passed that, I don't know, let's call it 100 years had passed, still 13,000 people are going to know the rumor. Let's say 1,000 years passed, all right, and it never left this college campus. Still, only 13,000 people would know the rumor. So this introduces what's called an upper bound on the model. And because we have an upper bound, this limiting value, this 13,000 people who can know this rumor, we don't have exponential growth anymore because we start growing really quickly, and then around halfway to the carrying capacity, we start slowing down because we're reaching the limit. Fewer and fewer new people will be able to hear the rumor because we're reaching almost all 13,000. All right, so this suggests a logistic model. This is the whole idea behind a logistic model.